All right, recording is rolling. Welcome to Tuesday, April 11th. So you guys remember yesterday we did a couple of Kahoots. And today and tomorrow we're going to do a Kahoot each of these days. Right? I just gave you guys a packet of questions. You guys, these packet of questions. Right? The first page, double-sided, is all of today's questions, and the second page, again double-sided, is all of tomorrow's questions. I'll I'll do a review with you guys on Thursday. We'll do some circuits, and then on Friday the quiz. Open nose. I told you guys yesterday is going to be here mostly questions from this packet. Right, so questions that you see on the Kahoot today and tomorrow. Going to show up in the quiz, and I'll also draw you guys a circuit, and I'll ask you guys a couple of basic questions about the circuit. Well, a couple of questions I think you should get if you've been following along. Okay, right? So everybody good with that? What's going on? Yep, that's just for you. Yeah, just for you. Okay, that's good. All right. So I flip over here. Yeah, so you guys are all ready to go. Got your laptops out, logged on. Awesome. All right. And here we go. Electric current. In order for there to be a flow of charge from one place to another, there must be yeah, both the above. Right. So the blue one, potential difference. For example, a battery has some kind of voltage, right? That's what potential difference is, voltage. Okay. But then you also have to have a conductor like a wire to connect the two places. Okay. Right. And then that'll set up some kind of current. Right. Both above. All right. Got points on the board. And solid conductors, electric current is the flow of electrons. There you go. Right. Electrons are on the move. Right. Now you guys know direct current, there is a net motion of electrons. And in alternating current, the electrons just move back and forth. There's no net motion, but the electrons do move. The energy that way. All right. Uh, an ampere is, oh, well, sorry. To hop back in and be best. Yeah, unit of current, right? So you guys know unit of guys. What's the unit for resistance? Ohms, right? Greek letter omega, ohms. Right? Current. The symbol for that is capital I, and the unit is amps or ampere. And charge is in coulombs, right? Guys know that? Right. Coulombs per second is current amps. Example of a voltage source. Yeah, so all those could provide some kind of potential difference, which would be a voltage, right? Anytime you charge something up, right, something has a charge on it, well, there's some energy per charge. That's also what a voltage is, right? Potential difference. You're quantifying volts. There you go. Electrical resistance in a wire depends on the wire's what? Nice, all the above, right? Real fast, I'm gonna flip my screen just to remind you guys this, in case you forgot this. You guys want to do that Play-Doh lab? Play-Doh, you're trying to figure out what's the resistivity of Play-Doh, right? So the resistance of a wire end to end, right, depends on its length, right? The longer the wire, the more resistance. Cross-sectional area, I think the answer choice was thickness, but that plays into that idea, right? I think another answer choice was conductivity, which is just the reciprocal of resistivity. So same idea there. Right. So you guys get. So that was you guys' Play-Doh lab. It's the resistivity of Play-Doh. Right? So resistivity is a material property, right? So copper, aluminum, Play-Doh. Right? Resistance is how many ohms and in. Is this frozen? What just happened? Oh, all right. Timeout. All right, I'm gonna have to pause this. Pause. Sorry about that, guys. Okay, so we're back. All right, we just had a screen freeze there. And so compared to thin wires, the electrical resistance and thick wires, right, I know you guys couldn't see the answer, but just flip my screen over here and remind you guys how this works. Okay. So if you have thick wires, wouldn't that be a huge cross-sectional area? Okay. Which means that thick wires have less resistance, divided by large enough, right? Okay. And thin wires would have more resistance. Okay. It's harder to push electricity through a thin wire than it is a thick wire. Thick wire, it's kind of easy. So thick wires is less resistance. That's okay. All right. Turn on. For most conductors, as their temperature increases, what do you think happens to resistance? Hmm. Oh, good call. Because I didn't actually tell you guys that, but that's true. Like as you heat things up, it's harder to send a current through. Right? When we get to quantum mechanics, I'll actually show you guys. Scientists made conductors colder, and at some point they hit a critical temperature and actually dropped to zero resistance, which is really it's called superconductivity. So yeah, the colder, it's easier to transmit a current. Right? And if it's warmer, then not as good. Right. All right, go back in the future. Electrical resistance measured in. Yeah, ohms. Nice. Right. Let's go over all these. Guys, what does joules measure? How much energy? Energy measured in joules. You can also say work or energy. Amperes measures current. And we pick that. Volts. Yeah, voltage. We could say potential difference. That works too. Yeah, resistance is measured in ohms. And Greek letter omega, a lot of times we used to represent ohms. Woman experiences electrical shock. The electrons making the shock come from where? Uh, oh, okay. Also, if you said from her, right? Please skip over and show you guys what's going on here. Right? So let's say I have a switch here. Right? Try to kind of draw this right, and a wire. Right? Maybe the switch is like yeah, so it's like a switch looks like this, right? But then you hit, so it was off. Now you bam, turn it on. So click. Right? It's gonna close this. Right? So quick creates a closed circuit, and now we got electricity flowing. Right? Let's say I have a light bulb like right here. Here's my light bulb. Right. It's got a filament in it. Right. Lights up. Bing. Right. You guys see all that, right? Right. Now, if you were to watch the actual electrons, I could do this room right here. So demo. Right. Turn off the lights. Right. And then flip them on. Bam. Okay. Now, for that electricity to light up those lights, what path was it traveling? Well, if you look at all the individual electrons, right? I'm drawing them way bigger here than they actually are, but just to give you the idea, right? The electrons might do something like this and then go up here. This is the resistor, it's part of your circuit right there, right? The electrons continue on their happy way. All right, electrons, boom, there you go, right? Right. Now, do the electrons immediately race through the bulb like near the speed of light? No. Actually, all they do is they like push. They push against each other. So it's like a giant train. So you hit the on switch, there's 120 volts here, and then I'll start pushing. And the electrons themselves actually move really slow. Actually, if it's alternating current, they don't move on that at all. If it's alternating, they just like shake back and forth, and they transmit the energy kind of like a wave, right? But if it was direct current, like if I had a battery, let's suppose I have a battery, like this guy is hook this up like that. Right? The electrons just scooch. They all get pushed very slowly. Right? Now, how slowly is actually one of the questions coming up. So I want to see if you guys can get that. Okay. You guys good with that concept? Oh, okay, so if you were receiving a shock right here, just to tie that back to the question then, suppose you jam something electrical outlet. Obviously, don't do that. Right? But if you did and you got a shock, there's a motion of electrons through your body goes like, that's it. The electrons just go like through you, right? It's not electrons actually like from the wall necessarily. It's just the ones that are already contained in you, and everything just shifts because there's a potential difference between that wall socket and the ground. 120 volts. Primary reason a bird can perch harmlessly on bare high voltage wires without getting harmed. Yeah, there's no potential difference across the bird's feet. All right, so let me draw this out for you guys. So here comes a bird. This guy's gonna land on the wire, reach around, grabs that wire there, grabs the same wire right there. Okay. Guys, there's 100,000 volts, 100,000 volts. What's the potential difference? I'll write it as delta V. Sometimes I write it this way. What's the difference between 100,000 volts and 100,000 volts? There you go, nothing, 0 volts. If there's no voltage, right, I know current is the potential difference divided by the resistance, right? The bird has some resistance, right? Probably could conduct electricity, but yeah, if there's no voltage, there's no current. So bird's okay, right? You need a potential difference for a current to set up. Oh, yeah. Right. Well, if he has one foot in the air, then again, there's no like closed circuit could happen. So. Well, supposedly, probably wouldn't try that, but at least according to that question. All right. All right, yeah, okay, let me hit those last two questions also. But right. Alternating current, how do you make that? By altering the direction of the voltage at the point of the power source. Okay. Let me flip my screen over and show you guys a couple things here. Let me go back to the bird because there's another question about the bird. Okay. So what if there's a nearby tree? Right, so tree right here. Right, and it has a branch out here. Right, and the bird's like, hey, I'm gonna put 1 foot on this 100,000 volt wire and put my other foot right here on this branch. Now what happens to the bird? Chicken dinner, right? Right, because now there is a potential difference. Now is a current. Okay. Right, and then the question you guys just saw with alternating current. Okay. Here I've got this diagram for how three-phase alternating current works. So I know there's a green wire, a red wire, and a gold wire. Right? You guys see like 3 pairs of corresponding inductors. Hold on. Okay. Let's just focus on the gold wire, just to focus on, right? Okay. So this magnet's rotating, magnet's rotating, connected to a turbine probably. Okay. And that's going to push electrons one direction. When the north swings by, maybe it pushes electrons one way. But then the south swings by this one and pulls them the other way. Okay. And then the magnet keeps rotating, so that it goes back and forth. So here's what the electrons do. Shoo, 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 right? And there's no net movement of these electrons. Now you could transfer the energy, kind of like transferring energy on a wave, right? There's no net motion of the particles, right? It's just like pulsing, right? And then if you look at the voltage would be alternating like that. Hence alternating current, because the voltage is alternating. The point of the power source. Frequency of alternating current in North America. Frequency. Yeah, there you go, 60 hertz, 60 hertz frequency. Right. There's a trick answer on here, which is 120 volts. You guys know the potential difference, 120 volts, but that's not the frequency, right? Frequency, 60 hertz. Right. If you go over to Europe, it's probably 50 hertz, but here it's 60 hertz, right? Current from a battery is always direct current. There you go, direct current, right? So the electrons actually do flow and have net movement. If you have anything hooked to a battery, if you have a flashlight, if you have a clock, right, anything like that. Your phone, if you have a phone, laptops, you guys got, That's all batteries. That's all direct current. The electrons are actually have a net motion. Right? Now, if you plug in something into a wall socket, that's where it's alternating back and forth. So batteries, direct current. It's like their constant voltage. The net, oh, here we go. Net speed of electrons in a wire. I haven't told you guys this. Take your best guess. How fast are the electrons actually moving? So like in a flashlight, for example, in a flashlight. How fast? Best guess. Ooh, okay. So four of you guys did get that correctly, right? 0.01 centimeters per second. Is that like 0.1 millimeters per second? Okay. Let's flip back over here. That goes along with actually this picture I drew earlier, right? So when you flip the on switch, right? Now if it's alternating current, they'll actually just be going back and forth. But let's say this is like a flashlight, right? This is a flashlight. The electrons are moving really slowly, right? Moving really slowly, right? Okay. 0.1 millimeters per second. Here's 1 millimeter. You guys know 1 millimeter is a little tiny. So 1/10 of that every second. So it's still extremely slowly, but they're all pushing across, like moving the whole train of electrons. So, Griffin term. What's that? Is that all right? Now you know. All right. Where do the electrons come from that produce heat and light in a light bulb? Ooh, in a light bulb. Yep, the bulb's wire filament is the best answer. Okay, so flip back over here and trying to guess why. Okay. Actually, the question before this will help answer that question, sort of. I mean, if the motion of these electrons individually is like 0.1 millimeters per second, now it's an equation that links to that. That's kind of a middle number, right? And this filament itself is probably about what, a centimeter or two long, right? Yeah. Now, if it's direct current, then there's motion of these electrons through the filament, but the electrons in the filament themselves are lighting up, right? And if it's alternating current, then it's definitely only from the filament because the electrons are just going swish, 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 right? If it's alternating, right? Yeah, the electrons are already there, right? Kind of similar to a few questions ago. They're saying like if a person like jams something in an electric socket and gets a shock, right? But obviously don't do that, right? Then the electrons are already in you. They're just put in motion. Right? That's the electric current. Uh, the number of electrons delivered to an average American home by an average power utility was zero. There you go, right? Because that is alternating current. So the electrons just move back and forth, back and forth. There's no net motion. They stay pretty much the same place every day, every year, just back, forth, back, forth, back, forth, transmitting energy that way. Yeah. Alternating current. When you say that an appliance uses up electricity, what does that mean? Nice, nice. All right, so electron kinetic energy is changed into heat and other forms of energy. So that say if it's alternating current, that back and forth motion of electrons, right? There's some energy there. How much energy? Well, what's the voltage? Because it's voltage is energy per charge, right? So that'll tell you how much. Uh, the current doesn't actually disappear. You guys know any current that goes through a resistor, the current stays constant, right? Like if 3 amps goes through, it's 3 amps before and 3 amps after, right? So the current is conserved, right? That's like conservation of charge. Right? The voltage drops, right? But that goes hand in hand with the red answer, right? Because energy per charge would drop. That all right? So the kinetic energy motion of the electrons transferred into, well, other forms of energy, whatever you want to do. Plug in a toaster rated at 110 volts into a 220-volt outlet. What will the current be? Yep. Twice as much as what it should have been. Let's switch back over here. Guys, when you buy any appliance on the American market, it's made for like North American outlets. Right? So you go buy a toaster. Right? Now the toaster has some particular resistor in it. Right? That's just like built into the appliance. Right? But that's so that if you hook it up to 120 volts, some current will flow and the whole thing works. Right? Uh, but let's say you take that toaster over to England that has twice the voltage. Guess if you got twice the voltage that's supposed to go through the same resistor, you get twice the current that you're supposed to. It's going to overload it. Not going to work. Maybe that's what happens. Probably something not good. I should have answered that question. I don't know. Wouldn't be good for it though. Be careful about that. Electric power defined as current times voltage. Current times voltage. Right. There are two other answers that could have worked that are just not choices up there. But let me switch my screen over and you guys. Right. So how much power? This is Joule's law. Right. So Joule's law question: how much power? Current times voltage. Okay. Because we're filling out those Kirchhoff tables, and that was the last column of the. Oh wait, I think I got some right here. There you go. These Kirchhoff tables. So what's the power through each particular resistor? And this is exactly how I solved it. Okay. Now you could also combine any of these with Ohm's law, do some substitution, and get like any of these three versions of it. Current squared times resistance, voltage squared divided by resistance. Okay. Those all work also. Okay. If any of those had been offered as answer choices, then they could have been correct. But current times voltage is a great answer. There you go. Compared to the filament thickness of a 60-watt light bulb, the filament thickness of a 100-watt light bulb. Yeah, the thickness would be greater. If it's greater thickness, that's less resistance. So, oh, okay, almost everybody got that, which is awesome. I do want to point this out here. So let's say we were using this right here, 60 watts versus 100 watts. That's different power ratings. Okay? Now it's the same voltage source, maybe 120 volts, for example. So that's the same. Okay? So if you want more power, you have to have less resistance. Okay? You have to combine that with this right here. How do you get less resistance? Oh, greater area, cross-sectional area, and that would be greater thickness. Boom. Okay. When you build a light bulb, really the feature of the light bulb that pops up in those equations really is like the resistance in the resistor and some number of ohms. They might stamp on it like how many watts it is, but that corresponds to some voltage input for some particular market. Power outlets in our homes, North America, typically have a potential difference, not frequency, potential difference. All right, nice. Yeah, so 120 volts, right? 240 volts is the European standard. 60 hertz is the frequency, right? And then however many amps flow, well, that depends what you have plugged into it. So yeah, 120 volt outlets is what we've got in this room. That's the potential difference. 12-volt battery connected to a resistor. 2 amps flow through the resistor. What is that resistor's value? All right, nice. 6 ohms. 6 ohms. Okay, flip back over here. Solve this for you guys. Okay. So we're talking about Ohm's law. Okay. So they gave you 2 of these 3 things, right? It's just okay. So I like this fraction form. Current is caused by a voltage acting on resistance. Some textbooks write it this way: V equals IR. Okay? And we're solving for R, right? So what is R? Okay? They gave you 12 volts, and they said 2 amps end up flowing. So there's some resistance that's associated with. Divide 2 down. Resistance is 12 over 2 volts per amps. That's 6 ohms. You guys see how it works? Right? 6 ohm resistor. Current through a 10 ohm resistor connected to a 100-volt power supply. All right, nice. 10 amps. Almost everybody got that. So I'll show this real fast. Okay. That's just straight up that. You don't even have to do any arithmetic. Right? It's just that, isn't it? Okay. So current is voltage on resistance, 100 volts, 10 ohms. Divide those two. That gives you 10 amps. Boom. Done. Next. Ports. What is the resistance of a toaster that uses 2 amps when connected to 120 volts? They go 60 ohms. Right, switch back over here. Okay. Right, so again, this is just Ohm's law again. They gave you 2 of these 3. Okay. So we're solving for resistance in this case. Okay. It's at 120 volts for the potential difference. 2 amps ends up flowing. Well, it must have been 60 ohm resistor that made that happen. Okay. See that? When connected to 120 volts, how much current is in a light bulb that has a resistance of 360 ohms? Yeah, a third of an. Oh, okay. Sorry. Maybe that wasn't enough time. Right, a third of an amp. Right. All right. So switch over here. All right. So we're still with Ohm's law. Right. How much current flows? We've got 120 volt. We got 360 ohms. Right. So divide those two. That gives you uh, a third of an amp. Okay. Ooh, let's do an extension question. Can you guys say power is current times voltage, right? Or some version of Joule's law. We got 0.33 amps, so a third of an amp. We got 120 volts. Would that be 40 watts? Is that right? Right. So if you buy this light bulb in the store, what it probably looks like is filament. Hold on. Okay. It probably says 40 watts stamped on the top of it. 40 watts. Okay. But you guys know that it only is going to correspond to 120 volt source, right? And really, there's this filament has a resistance of 360 ohms. That's what makes it a 40 watt light bulb, right? Okay. So what's going on? Yeah, thank you. Yeah. All right. You guys got that? Right? There's the voltage source. There's the resistance. What's the current? All right. Yeah, it's a tiny, tiny, tiny current. All right. Everybody got that, but just to flash the numbers up here. Ohm's law, right? What come out to 20 on 110,000 is 0.0011, and that'd be amps. One right there. All right. Nice. How much power is used by a 6-volt flashlight battery that draws 1/2 amps of current? All right. You guys might need more time for these, but oops, sorry about. Yeah, 9 watts. Some of you guys got that. 9 watts. Oh, to flip back over here. Right. Now we're on to Joule's law. Right. Uh, if you know one of these and Ohm's law, you can combine them to get the other two. Right. So let's just use the top one because they told you current and voltage and asked for what is the power. Okay. So they said 1.5 amps of current, 6-volt voltage source. Okay. Multiply this together, 9 watts. 9 watts. Okay. That's the rate of energy, 9 watts. P equals IV. Power is current times voltage. Take care of that. When plugged into 120-volt wall outlet, how much current is used? Light bulb rated at 200 watts. Yeah, I do need to add a little bit more time to that question too. Right. I think it was like 1.67 amps I was getting. Okay. Let me flip over and show you guys. So you can still start with P equals IV. You have to, in this case, you have the power and the voltage, and you're solving for what is the corresponding current. Okay. So you divide those two. They confirm what that comes out to. What is 200, 120? Okay. Is, no, sorry, 200, 120 is 1.67. And then that's amps because it's a current. Okay. You guys can do that. Joule's law. Let's rearrange Joule's law a little bit. That right there. Everybody right? 100-watt light bulb connected to 120 volts. How much current? Yeah, okay. Yeah, that was a pretty fast too. Yeah, I got the same thing, 0.83 amps. I got that just in time of cell. Okay. Flip over. What did I just do? Did I just, all right, here we go. Okay. So this is I think similar structure to the last one too, right? If you divide those two. So you start with that, rearrange it like that, solve for current. It's like 0.83 amps, I think it comes out to. Yeah, thereabouts. Share. All right. Okay. Oh yeah. On the point screen. Points. Oh yeah. Oh, got 120-volt outlet, 0.4 amps current. What is the power rating of that light bulb? Ooh. Yeah, nice. 48 watts. Okay. So okay. This is just yeah. Right, straight P equals IV. Power is current times voltage. Got that. Okay. There's the power, or sorry, there's the current in amps. There's the potential difference in volts. Okay. So it's like 48 watts. Okay. Okay. So you might see a light bulb. It has stamped on it 48 watts. Okay. But you know what? I want to know one more thing. I want to know what is the actual resistance in this filament right here? What's the actual resistance? You guys figure that out. What's the resistance? Okay. Let's try to solve that. Are you guys getting 300 ohms? You guys get 300 ohms, right? I think I did that right, right? Right. That many volts, that many amps, right? Right. So there's like a 300 ohm resistor here that makes everything else work out. I'm going to do one more confirmation because Joule's law says that these also apply to you, right? Let's check out that last one. What if you take this 300 ohm resistor, and you plug it into 120 volts? Shouldn't the power be, well, also that answer? Right. Let's see if it is. If it is. Right. So I've got 120 volts. Square that. Divide by 300 ohm resistor. Right. And I better get 48 watts. Boom. Guess it's like the same thing. Right. Guess that. So different perspectives that they all work. Ooh, double points. Double points. Electric heater rated at 300 watts, 120 volt circuit. Circuit breaker can only handle up to 12 amps. How many heaters can safely be operated? All right. I see you said four. That was a complex type question. So take a look here. Okay. So they told you the power rating and the voltage source. It said that's the power rating of the toaster. That's the voltage source. Okay. So a single toaster is going to draw this many amps. Use Joule's law. That's Joule's law. Rearrange it that many amps. Now that's for a single toaster. Every toaster that you hook up to the wall now is going to draw more and more amps, more and more current. And we're going to max out at 12 amps. So I did a dimensional analysis table. Guys like this dimensional analysis? We can go up to 12 amps. That's like the budget. There's 2.7 amps per heater. That's rounded a little bit, but it's okay, it works out. Okay. Comes out to like 4.4 heaters. Okay. Well, you can only have an integer number of heaters, so you can fit up to 4. And then once you put the 5th heater on, now it's going to overload it. You see that? So you can fit up to 4. 4.4 integers, right? Whole numbers. Still rolling. Okay. 22 amps when connected to 110 volts. 10 cents per kilowatt hour. What's the cost for running for 12 hours? Oh, nice, nice. So you guys got that, and that is the majority count right there. So, uh, some serious legitimate about that too. So this is a pretty tough question here. Okay. So they told you the current and the voltage, okay, which means that you can calculate the power using Joule's law. You say, well, every single one of these is going to pull so this appliance pulls 2420 watts, right? So like over 2000 watts. Right? You have it plugged in, it's always pulling 2000 some watts, right? That's a continuous rate, joules per second. Okay? All right, so then dimensional analysis table. Well, I know that there's 1000 watts in a kilowatt hour. So watts, or sorry, whoops, 1000 watts in a kilowatt. That's what I meant to say. Okay, right, back to 1000. Right? Um, every kilowatt hour is 10 cents. Now I set it up this way, this fraction, so that the kilowatts cancels out. Right? And now you have a unit of money, but you also have a unit of time. So the last thing you say, well, they have to tell you how much time you run it for. It's like 12 hours. Right? Isn't like actually it's a version of this. Energy is equal to power times time. Yeah, so it's actually a bit formulaic. It's not strictly dimensional, like a conversion, right? But the hours cancels out regardless, right? It's because it fits that format, right? So that tells you how many dollars. We got $2.904. Okay, right. So that rounds to 291. If you round up, it's like 291. Okay, that's good. All right, last question for the win. Power line, 2 ohms, 70 amps. What's the power? Can you guys do I squared R? I squared R? Everybody's doing I squared R, right? Power is I squared. So that's 70 amps squared times 2 ohms. I squared R. Should be 9,800 watts. Oh yeah, that's what you guys got. 9,800 watts. Right. So flip the screen real fast. You guys can see exactly what I did. I just did current squared times resistance. Also tells you power. All right, back over here. All right, to the winner podium. All right, so hang on to that packet. We're gonna do more tomorrow with the bronze. Haley with the silver. Leroy and the gold. All 20. Unicorn. Runners up, Gina and Kent. All right, nice job, guys. Nice job. Oh yeah. Holiday day.